Alright, let's get right into it. Your assigned problems may or may not have different randomized values. For best results, attempt the assignment on your own before watching these solutions. Students are encouraged to frequently pause the video to work out steps on their own before proceeding with the solutions. And here's the list of topics to be covered in this video. So in this problem, we're supposed to multiply and simplify the expression, and we are given four options. Well, if we distribute root 10, we end up with root 10 times root 10 minus root 10 times 5. The square root of AB equals the square root of A times the square root of B, so these terms can be combined as the square root of 10 times 10 and the square root of 10 times 5. On the left, we have 10 times 10, or 10 squared, and on the right, we can factor 10 as 2 times 5. In other words, we have the square root of 10 squared, that's just the absolute value of 10, or 10, and on the right we end up with the square root of 5 squared, which we can just replace with a 5. So we have 10 minus 5 root 2, that's option C. In problem 2, rewrite the expression x to the negative 3/5 in radical form. Well, that exponent negative 3/5 I'm going to represent as negative 3 times 1/5 so that I can write this as x to the negative 3 all raised to the 1/5. Now that we have something to the 1 over a power, we can write that as the 5th root of x to the minus 3. Now let's write the 10th root of x plus 23 using rational exponents. There's not very much to do here. The 10th root of something is simply the 1 over 10 power, so there we have it. Problem 4, rewrite the expression the 15th root of x to the 13th using a rational exponent and no more radical sign. Well, the 15th root of something is that thing to the 1 over 15 power, so we have x to the 13th all raised to the 1 over 15. Now we're going to use properties of exponents to say that something to the 13 raised to the 1 over 15 power is that number x to the 13 times 1 over 15, or simply x to the 13 over 15. In problem 5, we're asked to simplify the square root of 125 x to the 15th divided by the square root of x to the 6th, and we're given four options that might be the simplified version. So first I'm going to take that numerator of the square root of 125 times x to the 15th and split those off as two radicals. I just want to deal with the variables and the constants separately. 125 is 5 cubed. Now every term, what we're going to do is find the largest even power we can to factor out. So out of 5 cubed, I can factor out a 5 squared, leaving behind a 5. And out of x to the 15th, I can factor out x to the 14th, leaving behind an x. Why would we factor out even powers? Well, we're going to exploit properties of exponents. So that square root of 5 squared times 5 gets broken up as the square root of 5 squared times the square root of 5. Similarly, the square root of x to the 14th times x is being broken up into two terms, and instead of x to the 14th, we're going to call that x to the 7th squared. Down in the denominator, that x to the 6th is being rewritten as x cubed squared. Why would we do this? Well, the square root of something squared is its absolute value. So first, the square root of 5 squared is the absolute value of 5, but that's just 5. The square root of x to the 7th squared is the absolute value of x to the 7th, and down in the denominator, the absolute value of x cubed is the same as the square root of x cubed squared. This absolute value step is frequently gotten wrong, but it is quite important to account for what numbers may or may not be negative. If x is negative, x to the 7th and x cubed are both negative. However, two steps above, we had x to the 14th and x to the 6th, and those will not be even if x is negative. So now what we have, we've taken the square root 5 and the square root x and recombined them as a single radical. Now we have the absolute value of x to the 7th over the absolute value of x cubed. That simplifies down to the absolute value of x to the 4th. Now whether x is positive or not, now the absolute value is redundant. If x is positive, then x to the 4th is positive, and if x is negative, x to the 4th is still positive. So now we can drop the absolute value, and we have 5 times x to the 4th times the square root of 5x. However, it's important that this is only true if x is not 0. Down at the bottom line, x equals 0 looks like a perfectly legitimate expression, whereas in the line above, it's clearly not. So option D is listed as correct in the original assignment, but it looks like it's including x equals 0 in the domain, whereas x equals 0 is definitely not in the domain of the original expression. This expression is the same for all other values of x and clearly indicates x equals 0 cannot be in the domain. Now the absolute value doesn't show up here. That turns out to not be so important because, as we discovered, the absolute value of x to the 7th over the absolute value of x cubed is the same thing as x to the 4th, which is what you could simplify this down to. Okay, but this isn't quite simplified. Does that mean it's more correct because it indicates that 0 is not in the domain, whereas option D seems to include 0 in the domain? I don't know. I do think the best solution is just to write 5x to the fourth root 5x and specify that x equals 0 is not in the domain. In problem 6, the radical, fourth root of sixth root of square root of x simplifies how, and we're given 5 options. Well, the fourth root of something is that thing to the 1/4, the sixth root of something is that thing to the 1/6, and the square root of something is that thing to the 1/2. So we have x to the 1/2 all raised to the 1/6, all raised to the 1/4. When you have exponents stacked like this, one thing to another power, and then all of that to another, etc., the exponents multiply. So we have x to the 1/2 times 1/6 times 1/4, aka x to the 1 over 48. That's the 48th root of x, which is exactly option E. In problem 7, simplify the expression 7th root of x times the quantity 7th root of x to the 6th minus 7 times the 7th root of x to the 4th. I prefer to switch all of these to fractional exponents rather than radical notation. I find it easier to work with. So we have x to the 1/7 times x to the 6th raised to the 1/7 minus 7 times x to the 4th raised to the 1/7. We have x to the 6th to the 1/7 and x to the 4th to the 1/7. I'm going to multiply those exponents. So now we have x to the 1/7 times the quantity x to the 6/7 minus 7 times x to the 4/7. We can distribute that x to the 1/7 out. And now we can start combining exponents. If we have x to the 1 over 7 times x to the 6 over 7, we can add those two exponents. And similarly, x to the 1 over 7 times x to the 4 over 7, we can add those two exponents. There's no common denominator to find here. It's all sevenths. So we have x to the 7 over 7, otherwise known as x to the first, minus 7 times x to the 5 over 7. If radical notation happens to be preferred for whatever reason, that x to the 5 over 7 can be replaced with the 7th root of x to the 5th. In problem 8, we're going to be given several equations and asked to determine if these functions are odd, even, or neither. First will be f of x equals x squared, second g of x is x to the 1/2, and third h of x equals 3 over x. To determine if a function is odd or even, you replace x with minus x, and essentially you see what happens. So f of minus x would be minus x squared. I'm going to write that as minus x times minus x, which can be factored as negative 1 times x times negative 1 times x. In other words, negative 1 squared times x squared. Of course, what is negative 1 squared? It's 1. So we have f of minus x is x squared, which is the same thing as the original f of x. When f of minus x is exactly equal to f of x, that is an even function. If the minus sign essentially factored out and we had achieved f of minus x equals minus f of x, that's an odd function. And if neither of those things happen, well, that's neither odd nor even. In b, we have g of minus x, which is minus x to the 1/2. In other words, the square root of minus x. Now, if x is not 0, either x is positive and minus x is negative, or x is negative and minus x is positive. But regardless, between g of x and g of minus x, in other words, root x and root minus x, one of them won't even exist. So you certainly can't factor a minus sign out or ignore it. Neither of those things happens. This function is not odd. It's also not even. H of x, we're going to test out what is h of minus x. It's 3 over minus x, which is the same thing as negative 3 over x, but 3 over x was exactly h of x. So since h of minus x is in minus h of x, that's an odd function. The minus sign essentially factored out. Now let's match various graphs with various functions. Here we have a whole assortment of functions, and here we have a whole assortment of graphs. So instead of plugging points in and computing things, what we're going to look for is identifying behavior. For example, f of x equals x is a line. It has positive slope and 0 intercept. And looking at all of the options, there are only 3 lines, one of which has 0 slope, and 2 have positive slope, but one of them has a negative intercept. So positive slope and 0 intercept, the only option is I. What about x cubed? Since I'm raising x to an odd power, this is an odd function, and it's relatively quickly increasing. Compared to everything else up here, x to the third is a pretty large power. So I'm looking for an odd function, which graphically can be represented as reflection across the origin, and I'm looking for it to increase pretty quickly for positive values. So option A does not have this kind of symmetry, nor does B, nor does F or G or H. Option I is a straight line. What's increasing pretty quickly? Not D, but rather C. So C is the graph of x cubed. In contrast, Here we have x to the 1/3. This is still an odd function. We have 1 over an odd number as our power, but it's increasing rather slowly. That's going to be the graph in D. What about root x? Compared to everything else up here, this is the only one whose domain is exactly x bigger than or equal to 0, and that's the graph in B. F of x equals minus 2 is a constant, and there's really only one graph up here that's a horizontal line, that's G. F of x equals x squared, we recognize as a parabola that is opening up. There's only one option, that's H. F of x equals 1/2 x minus 2 is a straight line. Its slope is positive, 1/2, and it has a negative intercept, and that's f right there. What about f of x equals 1 over x? The domain is everything other than 0, so we're looking for a graph that contains every x value except for 0, and that's this one right here at E. And the absolute value function has this classic V shape that we'll simply learn to recognize as time goes on. Also, it's the only one left, it's A. For problem 10, find the domain and range of the function given this graph is correct, and use interval notation for your answers. So for the domain, what we want to do is look at the x values of a function, in other words, vertical lines. So here, for example, is x equals minus 4. It does intersect the graph, meaning it is in the domain. So how far to the left can x go? All the way to minus 9, and that is included. And how far to the right can it go? It just keeps going. In other words, we can include everything from negative 9 and bigger than that. So that's the interval from negative 9 to infinity, and we include negative 9. An alternative way to do this, the only restriction in the domain of the function is we have this radical. The thing underneath the radical cannot be negative, so x has to be bigger than or equal to minus 9. You'll get the same answer. This completely ignores the graph, by the way. We really don't need the graph to do this problem. Now let's look at the range. We're going to be looking at the y values, the outputs. Those are horizontal lines. So here, for example, is a value of y, a horizontal line. It does intersect the graph, meaning this value of y is in the range. Well, how far down can we go? Here's the bottom of the curve, and it does include that point, and that's at a height of negative 2. How far up does it go? It just keeps going. So we're looking for the range to be starting at minus 2 and then increasing without bound, and since it did include minus 2 in the range, we include it with a square bracket in this interval. Another way to do this is to say the square root of a thing can be any value bigger than or equal to 0. We have negative 2 plus the square root of a thing for our function, so the range of our function is bigger than or equal to minus 2. In number 11, we have three functions here, and we have three graphs. So f of x equals negative root x, f of x equals 3 root x, and f of x equals 1/2 root x. So they're all radical functions, but we're going to be looking for what we can use to distinguish one from the other. Well, the only one that produces negative outputs is the first one, so that's got to be this graph here. It's the only graph with negative y values. Between the other two, let's actually pick a test value. An easy thing to take a square root of is 1. For b, we get 3 times the square root of 1, in other words 3. So plugging in x equals 1, we got an output of 3. So we're looking for which of these graphs contains the point 1, 3, and it's the one on the right. So that's the graph of 3 times root x. If we tried plugging 1 into option C, we would get 1/2 times the square root of 1, or 1/2. So we're looking for a graph that contains the point 1, 1/2. And there it is. So this is the graph of 1/2 root x. In problem 12, we're going to find 5 solutions to the equation y equals cube root x minus 2, and then we're going to plot them and use that to make a graph. And the values of x that we're told to use are negative 8, negative 1, 0, 1, and 8. What's really helpful to know is that 2 cubed is equal to 8, and negative 2 cubed is equal to negative 8. In other words, 8 to the 1/3 power is 2, and negative 8 to the 1/3 power is minus 2. So if x is negative 8, we have negative 8 to the 1/3 minus 2, which is negative 2 minus 2, or minus 4. So when x is minus 8, then y must be minus 4. So the graph contains the point, negative 8, negative 4, so we put down that point. If x is minus 1, we get y equals negative 1 to the 1/3 minus 2, which simplifies down to minus 3. So the graph must contain the point negative 1, negative 3, so we put that down here. When x is 0, we get 0 to the 1/3 minus 2, or just minus 2. So the graph must contain the point 0, minus 2, so we throw that down. When x is 1, we get the cube root of 1, which is 1, In other words, the graph must contain the point -1, -1. There it is. When x is 8, we get 8 to the 1/3, which we know to be 2. 2 minus 2 is 0. So the graph must contain the point 8, 0. So we put that down. And now we just need to join these points together with a cube root-ish looking kind of thing, and there it is. This really is just the standard graph of the cube root of x, but it's been shifted down by 2, matching that y is the cube root of x minus 2, a vertical shift of 2. Problem 13. This is the graph of a function, which is a transformation of root x. Let's find a possible equation for the function graphed, and different people may end up with slightly different looking solutions. Algebraically, they should all be equal, but they may appear slightly different. So one approach that we're going to take is we're going to start with the standard graph of y equals root x. Here we have it in red. If we horizontally reflect it by replacing x with minus x, this is now a little closer. It's going in the correct direction. We're going to shift it to the right 2 units by replacing x with x minus 2. Be careful about that minus sign we've already introduced. Then we need to shift it down 2 units to achieve exactly the graph we were looking for, with y equals the square root of negative x minus 2 all minus 2. In problem 14, we're going to write an equation for a function that has the same shape as y equals 5th root of x, but it's been shifted right 4 units and shifted down 3 units. So first, let's shift right 4 units. Instead of x to the 1/5, we're going to shift right by replacing x with x minus 4. Then to shift down 3 units, we simply subtract 3 from the entire expression. In problem 15, for each of the given functions, we want to write the domain as both an interval and as an inequality. Now, every row involves a radical, so all we need to solve is the thing under the radical, the thing we're taking the square root of, must be non-negative. Just remember that when you have these inequalities, if at some point you multiply or divide by a negative number, that will reverse the inequality. So first, let's look at f of x, the square root of 10x minus 16. So the thing under the radical must be bigger than or equal to 0. We add 16 to both sides. We divide by 10. There we have it. Okay, we can simplify 16 over 10 as 8/5. So there's our inequality. X must be bigger than or equal to 8/5. As an interval, we want to include 8/5 and then go to the right, bigger than or equal to 8/5. For g of x, the thing under the radical is negative 6x minus 20. We need that to be non-negative. Add 20 to both sides, divide by negative 6, and then simplify. Observe that we have reversed the inequality because we divided by a negative number. So x must be less than or equal to negative 10/3. So there's our inequality. X is less than or equal to negative 10/3. As an interval, this goes to the left, off to minus infinity, but then it goes up to negative 10/3 and includes it. X is less than or equal to negative 10/3. For the third row, which is also f of x, again, we're just going to set the thing under the radical to be bigger than or equal to 0. We're going to add the constant 10. We're going to divide by 5. We do not have to reverse the inequality because 5 is not negative. We simplify this down to 2. X is bigger than or equal to 2. There's our inequality. And as an interval, we simply want to start at 2 and include it, and go off to the right to infinity. Finally, for p of x, the thing under the radical must be bigger than or equal to 0. Add 6 to both sides, divide by 15, simplify as necessary, and we have x is bigger than or equal to 2/5, so there's our inequality. And as an interval, it will start at 2/5 included, and then go off to the right. In problem 16, we want to identify the end behaviors of the function whose graph is given, assuming that the graph is accurate and continues as suggested. Of course, without an equation or without a graph that goes on literally forever, there's always the possibility it starts doing something else, but we're just going to assume that what is suggested is true. So on the right, we have as x goes to infinity, what is happening to f of x? Okay, that is the right end behavior. We want x to move to the right. So x is going to plus infinity. What is happening to f of x? Well, let's take this point and start moving it to the right in the x-coordinate and see what is happening to the y-coordinate. The y-coordinate is going up and up and up, and if it is accurate and it continues in this way, it goes off to plus infinity. What about to the left? Well, here's an arrow pointing left. That means x is going to minus infinity. What is f of x doing? Again, let's take a test point. We're going to slide it to the left and see what happens to the y-coordinate. Lo and behold, it's also going up and up and up, so f of x is going to plus infinity in both directions. Problem 17, very similar to the previous problem, identify the end behaviors of the function graph below, and we have to assume that what is suggested by the graph we have does continue in that way. So we need to look at right and left end behavior. So first let's look at right end behavior. So we're going to go ahead and put down an arrow pointing to the right. This means x is getting bigger, so x is going to plus infinity. What's happening to f of x? We'll put a point on the graph. As we slide to the right, what's happening to the y coordinate? It's going up and up and up, so f of x appears to be going to plus infinity. Again, we're assuming that the graph continues in this way and doesn't somehow change later on. What about left end behavior? We put in an arrow pointing to the left, meaning x is going to minus infinity. To see what's happening to f of x, we're going to take this point on the graph and slide it left and see what happens to our y coordinate. Oh, it's going down off to minus infinity. Now let's describe the end behaviors of x to the 7th. What's the right end behavior? What's the left end behavior? Well, right means x goes to plus infinity, and left means x goes to minus infinity. So we have a positive leading coefficient, 1 times x to the 7th. That will mean, in any polynomial, that to the right it goes to plus infinity. When we have an odd degree polynomial, it has opposite behavior in the two directions. So on the right, it went to plus infinity, meaning to the left, it goes to minus infinity. How about f of x equals negative x to the 6th? What are its end behaviors? Well, again, to the right means x goes to plus infinity, and to the left means x goes to minus infinity. Regardless of the function, that's just what right and left mean in our typical way of graphing things. Here, however, we have a negative leading coefficient, minus 1. For any polynomial, a negative leading coefficient means the right end behavior is negative infinity. But we have an even degree polynomial, x to the 6th. And an even degree polynomial will always do the same thing on both sides. So to the right, it's going to minus infinity. That means to the left, it's doing the same thing, going to minus infinity. For problem 19, we have a bunch of equations. We're going to solve them for x. I caution you that squaring both sides of an equation loses information about what was positive and what was negative. So if you ever solve something by squaring both sides, it's important to go back at the end of your work and check if your answer made sense in the original problem. So first, we have 2 times the square root of x plus 3 equals 4. We're going to divide both sides by 2. Now we can square both sides, canceling out that square root, and we have x plus 3 is 2 squared, aka 4. This gives us x equals 1. Does that work in the original expression? Why, yes. 2 times the square root of 1 plus 3, that's 2 times root 4, or 2 times 2, that is 4. So this checks out. So x equals 1 is the solution to the first equation. Second, the square root of 9x plus 8 minus 6 is 0. We're going to add 6 to both sides. We're then going to square both sides. We can now subtract 8 and divide by 9, solving x is equal to 28 over 9. But since we squared both sides at some step, we should check the original. Under the radical, we would have 9x, or 9 times 28/9, plus 8 minus 6. 9 times 28 over 9 is simply 28. 28 plus 8 is 36. The square root of 36 is 6, and 6 minus 6 is 0. This all checks out. So indeed, x equals 28 over 9 is the solution for the second. Third, we have 2 times the square root of 2x minus 3 equals 4. We're going to divide both sides by 2. We're going to square both sides. We're going to add 3 to both sides. We're going to divide by 2. So we've solved and we've gotten x is equal to 7 over 2, but we want to check if that fits the original equation because we did at some point square both sides. So we have 2 times the square root of 2x minus 3. 2 times 7/2 would just be 7. 7 minus 3 is 4. The square root of 4 is 2, and 2 times 2 is 4. This all checks out. So we found a solution, x equals 7/2. Fourth, we have the square root of 18x plus 14 equals the square root of 8x minus 17. We're going to square both sides, so we just have 18x plus 14 equals 8x minus 17. If we move all the x's to one side and all of the constants to another, we have 10x is equal to negative 31, or x is equal to negative 31 over 10. But now let's check if that works in the original. If we plug in negative 31 over 10 for x, what's happening under these radicals? This is not true anymore because observe, for example, on the left, we'll have 18 times negative 31 over 10. That's a fairly large negative number. 31 over 10, I'm going to round off to 3. So we essentially have 18 times negative 3. That's about negative 54. When we add 14 to that, it is still a negative number. So what's under the radicals will in fact be equal on both sides, but the number that they both are is negative and therefore is not a solution to the original expression. Okay, so under the radical, you'll have the same number. If you solve for the intersection of the lines, essentially 18x plus 14 and 8x minus 17, you'll find that x equals negative 31 over 10 is the value at which these two lines intersect. However, that value of x is not valid in the original expression involving radicals. So there's no solution to this problem. We fill that in. In problem 20, we want to solve the inequality. The square root of x plus 16 minus 5 is larger than minus 1. We're going to use the interval notation at the end of the day. So I want to caution you, you're going to be tempted to square an inequality to get rid of that square root sign. When can you square an inequality? When both sides are positive. If negative numbers are involved, squaring, which is just multiplying something by itself, means you are multiplying with negative numbers, in which case inequalities are trickier to work with. So be very, very cautious about squaring inequalities. Before you square an inequality, ask yourself, do you know for a fact whether the quantities involved are positive, negative, or are you just not sure? So here we have the square root of x plus 16. Minus 5 is larger than minus 1. The first thing we do is add 5 to both sides. No trick there. Now the radical sign, by definition, means the non-negative square root of something. If I write, for example, root 16, that just means 4, not minus 4. Root 9 is 3, not minus 3. The radical sign itself tells you this is the non-negative number. And on the right, we certainly have a non-negative number. It's 4. So both sides are non-negative. So I can square this inequality without worrying about it. So we get rid of the radical on the left, and on the right, 4 squared is 16. Cancel out the 16s. X just needs to be positive as an interval. That's from 0 to infinity, not including 0. In problem 21, are these two functions inverses or are they not? F of x is the cube root of x minus 4. G of x is x plus 4 cubed. Well, we've got a minus 4 on one side, a plus 4 on the other, a cube root on one, a cubing on the other. It's plausible at least. But what we should do is check, is f of g of x always equal to x, and is g of f of x also always equal to x? So first we're going to check f of g of x, the cube root of x plus 4 cubed minus 4. All we have done in f of x is replace the x with the expression g of x, which was x plus 4 cubed. Now x plus 4 cubed is x cubed plus 12x squared plus 48x plus 64. When we subtract the 4, we still have a lot going on here. This is not just going to simplify down to x. So we don't even need to check the other order of composition. These functions are not inverses. One of the orders of composition I checked did not give me the identity function. If you really did want to find the inverse function of f of x, it would not be g of x, x plus 4 cubed. It would simply be x cubed plus 4.